My to design a time-optimal trajectories for a unicycle-based robot. This is the outline of my project. The first part is the introduction of the problem. The second part is the kinematic model of the systems. In the third part, I will discuss the optimal control policies, the optimal time control policies, which can be given by the minimum principle. The fourth part is some results of the simulation, and at last, this is the future works. So the purpose of this problem is to design a time-optimal trajectory for a robot with two independent wheels move from the original point to a position with some configurations which involved the positions, the orientation, and the velocity. So the method the method used to solve this problem is based on the minimum principle. So this is apart from frame definitions of the robot. So VL is the velocity on the left wheels. The VR is the velocity on the right wheels. VC is the forward and backward speed. This is the ICC is the reference point, and this is RICC is the distance between the reference point to the center of the robot. So from this picture, the dynamic of the system can be written at this in these 5 equations. Now I will give example. Talk about how to move this robot rotate around a given point. This is a control input. So follow these control policies. This robot will rotating around the point with radius equals to 0.5. Here is another example. In this example, I try to move this robot from a given point, from the original point to a final point with some orientations. So these control policies can be divided into 2 different steps. In the first step, follow a well-designed control input. This robot will move to the final position on the x-axis with the right final orientation theta. But we cannot control the y to the right value in the first steps. So then in the next step, switch the control policy, and in this period, the value of y-axis will be fixed, and in fact the machine also rotates around its center, so the orientation doesn't change. Now I will talk about how to find the optimal control policy in this project. The previous 2 examples I showed are not optimal in both time and distance, and the speed of the wheels also need to be controlled. So now the purpose turns into that given the initial position x0 and y0 and initial orientation theta 0, move this machine to a final terminal to a final position xtf and ytf and theta tf with 0 velocities. These inequalities gives the constraint of the input. Since what I'm doing is to minimize the total time for the rotation, so the cost function can be written in this way. I also assume that all the states start from 0. To solve these problems, the minimum principle can be used. The first step is to write down the Hamiltonian function, which is given by the cost function and the dynamic of these systems. And the next step is to figure out the optimal control policies. The optimal control policies is given by following, which means that the equation 8 means that when the variable lambda 4 is negative, the control input on the right well need to take the maximum value in order to minimize the Hamiltonian function. So for the same reason, the other three control policies can also be found. These are the joint equations for the systems. In this case, solving the differential equations, it can be found that the dual variable lambda 1 and lambda 2 are equals to some constant which depends on the initial conditions. In order to simplify the computation of the dual variables, I assume that this relationship is needed, which is a function of x3. x3 means the orientation of this unicycle-based robot. So the next step is to figure out the trajectory for the dual variables. From equation 1, 2, and 14, 17, this differential equation can be obtained. Integrating it, we can find the relationship between the position x1, x2, and the dual variable lambda 3. To continue the computation, auxiliary variables vi are needed. The dynamic of a vi is given by these four equations from 20 to 23. The initial conditions for the auxiliary variables vi are 0 at the time 0. Then substitute these auxiliary variables back into the adjoint functions and integrating it. These two equations, we can have these two equations, which basically is a function of time. Since from equation 8 and equation 8 to equation 11, we know that the optimal control for this problem is band control. So which means that when the control, for example, when the control of the right well switched at some time, in this case, this equation, the value of lambda 4 needs to be equal to 0, and this equation, which means this equation need to be 0. So it is obvious that the number of the equations we get depends on how many times we switch, how many times the control policy is switched. So following this idea, we can have a bunch of different equations at different switching times. Then we can have this relationship, which is a lambda I0 equals to 0. Lambda I0 are the initial conditions for the dual variables. The value, the role of matrix A is determined by these two equations. In order to find the non-zero solutions for lambda I zeros, we need to make sure that the rank of A should be small or equal to 4, since we have 5 different unknowns in this case. So the rank of A should be equal or less than 4. Now let's talk about the relationship between the segments and the final orientation. In this project, I assume that switch time is for both whales. The control policies on both whales switch twice, and the direction of the initial acceleration is positive. So assume tau 1, tau 3, and tau 5 are the time segments for the right whale, and tau 2, tau 4, tau 6 is a time segment for the left whale. Indicating these two differential equations, we can have this function. We can have this relationship between the time segment tau 5 to the distance for right whale to move in the whole time interval given by 2t. Since the velocity of the robot is 0 in the end, and the control policy we used in this case is bang-bang control, the time for the acceleration should equal to the time for the deceleration, which means tau 3 should be equal to capital T, and tau 5 plus tau 1 also need equal to capital T. T is half of the total trajectory time. Now this is the relationship. This is the solution for the right whales. The solution for the left whales had the same structure. So using the equations, now use the equations from 26 to 28 together with the dynamic of the systems. We can get the relationship between the final control, between the final orientation and the time segment. In this case, if the final control is positive for all the whales, we can have this relationship. Adjusting the value of t for switch time trajectories can reach any final configuration. In the end, we can get the simulation of these problems. So with these parameters, the control policy and velocity on both of the whales looks like this. Here is the trajectories of the position and the orientation. This is the trajectory of dual variables lambda 4 and lambda 5. The future work about this problem is to analyze more cases with different initial conditions, which is the different direction of the acceleration, because in this project I only analyze the situation when the direction of the acceleration starts from positive. Another problem need to concern is the cases with different switch times, because the control policy can switch more than 4 times. This is the reference. Thanks.